course, it sounds ridiculous. It's absurd. And one can easily make several objections. I can think of 2 objections to saying that these free fall particles are inertial. For example, anybody want to suggest? We don't measure inertial forces, we know that. But what else, what other qualifications would be needed maybe for us to consider this to be inertial? Okay, well, one is the trajectory is certainly not a straight line. I mean, right, inertial trajectories should be straight lines. Another one is that, I mean, here I am standing on the Earth. I'm stationary, right? I'm inertial, right? Right now, not moving, I'm inertial, okay? I take something, I throw it up. I mean, I see it accelerating the whole time. This is accelerating. You can't tell me it's inertial. I am inertial. I'm not moving, and that was accelerating. So those are 2 simple disproofs. So should we reject this idea that gravitational free fall is basically inertial? Well, we think deeply into it. Einstein did, and he realized that one can easily overcome these 2 objections. If you imagine yourself in free fall and you're watching any free fall object, whatever the trajectory, I'll show you in a minute how you can see that all those trajectories are actually straight lines. I think it's absurd with straight lines. I mean, obviously it's curved, but think of it. If you're in free fall, right? Just for a simple case, let's make it free fall, meaning radial infall, straight down. And you're seeing some other trajectory which is clearly curved, right? Now, what's happening, imagine you're right next to each other, just to simplify matters. We're keeping the essential ingredients there. You're near each other and you're falling. Both of you are experiencing exactly the same acceleration. So as this is moving past you, it's going up with its initial velocity. It's also being accelerated downwards due to gravity, right? And you are being accelerated downwards due to gravity. If your acceleration is exactly the same, as it indeed is, then there is no relative motion between you other than due to the initial velocity. But that's a uniform motion. You have an initial velocity, whatever it was ejected out of a cannon at 1,000 miles an hour, whatever it is, in that direction, right? Making a curved trajectory. But at any point along that curved trajectory, if you're in free fall alongside it, for that instant that you're alongside it, it's passing you, right? For that instant that you're alongside it, then this particle has exactly the same acceleration as you do, and so that's effectively canceled out. You have equally accelerated forces on you. The relative motion due to acceleration is gone. You've eliminated it by free fall alongside it. And that's pretty amazing. So we've knocked off one major objection. But the other objection seems even more serious. So, it's very nice that you're telling me that in a free fall frame, this is a straight line, right? But what am I going to do about the observer stationary, who clearly sees that as accelerated? So Einstein's answer is... So what does Einstein say? If you feel the same thing and you measure the same thing, these states are completely indistinguishable, and therefore they are identical. In other words, there is no physical meaning to saying that we are not now accelerated. We are accelerated. We are accelerated. Because the system, in terms of what's measurable physically, is exactly that. Accelerated. Right? So it's like if you were inertial in empty space, far away from anywhere, and you are inertial, you have no inertial effects, and some spaceship goes by and the rockets are on and it's accelerated, and they're pressed back against their seat, they have accelerated forces, and they look out and say, you're accelerated. You look at them and say, I'm not accelerated, I don't measure any inertial forces on me. You say, well, I can see that you're accelerated. You look at them and you can see their chest is compressed. You say, you're undergoing acceleration. I see those accelerated effects. You're not an inertial frame. You can't tell me that I'm accelerated. I don't measure inertial effects. I see on you that you have inertial effects. And that's exactly the situation of gravity. Here we are, standing on the ground, feeling this push against us. And if we measure, we find out it's all the same accelerative push. And so we are accelerated. So we certainly cannot tell this free fall particle that it is accelerated. It's us. And that answers the second objection. So we had a free fall particle. In that free fall frame, there are equally accelerated forces, so no inertial effects can be measured. Everything is moving relative to each other with constant speed and so on. There's no inertial forces at all. The trajectories that each one will see, even if they're moving within that frame, will all be straight lines. And the frame which contradicts them and claims that they're not inertial experiences inertial effects, exactly identical to those of an accelerated frame. And so that's Einstein's model. He says, you take an inertial particle in free space, it's moving inertially, it enters into a region where there's matter, and it's affected by gravity, it's still inertial. It's still inertial. A gravitational field doesn't stop something from being inertial. It was inertial, it still is inertial. That's pretty astonishing.